see here, I think we are live. Well, welcome to Kopernik Observatory. My name is Drew Desker. I'm the director here. I want to welcome those watching on the live stream. And today's program is going to be about actually another nonprofit that is here in the area and doing some great work in the area of STEM. But I do see some familiar faces, and it's great to have you back here. And also some new faces. Actually, this evening we were also having people come up that are participating in our Rocket Fest to come up and pick up their rockets. And so one of our budding rocket engineers is here today, and you picked an excellent program to plug into. So anyway, Binghamton Makerspace we'll learn a little bit more about, has been around for a while and is, I think, does a real important job. I think, maybe I'm showing a little bit of my age here, but when I was in high school, shop class was sort of a required thing for me to take. Not so much these days, and I think it's important for people to know how to use tools and ultimately, either making stuff themselves or fixing stuff themselves. But I think we're going to focus more today on making stuff. And so what I'm going to do is I'm going to turn this over to Stephen. Is it Musok? Musok, who's the executive director of the Triple City Makerspace, and he's got a presentation that I'm going to go to. So if you give me a moment and get out of this mode and get into that mode, and hopefully there we are. All right, so Stephen, take it away.
All right, Drew, I'd like to thank you for hosting us in Observatory. My name is Stephen Musok. I'm the director of Triple Cities Makerspace. How many of you have heard of the Makerspace?
Hi.
I always ask that over the years. We're about to celebrate our 10th year in existence, so get more and more hands up. So if you could move to the
nice.
So we have a facility. We are on 362 State Street. We are a 501c3, not-for-profit, and we have a dual mission. First is to promote science, technology, engineering, art, and math. And then the second is to provide equipment and resources to the community to lower the cost barrier of entry to what can be really cost-prohibitive tools. Next slide. So, like a lot of businesses, we were shuttered during the pandemic, deemed a non-essential business. And so one of the things that the Makerspace did was we had a really big bank of 3D printers. And so from home, members of the board and members of the Makerspace partnered with the Southern Tier Face Shield Group to create PPE for the community. And we were able to create and distribute 5,000 face shields using our printers. We gave them away for free.
Right here in the Southern Tier.
Right here in the Southern Tier.
Wow.
To the next slide. So the Makerspace has a wood shop, has a metal shop, classroom, pottery kiln. We have 14 FDM printers, 1 SLA printer, a laser cutter, computer access with CAD and CAM software, Adobe Creative Suite, an MS Office Suite. We have a Haas mill, a Haas lathe. We have a lot more resources as well. And for our membership, we have 24-hour access to all of that. You can go in there anytime and use any of it, as long as you're signed off. To not be a risk to yourself or anyone else.
Very important, safety.
Yeah. But the real benefit of being part of the Makerspace is the people that you get to talk to. In order to access some of that dangerous equipment, we have an access control system, and you're given a fob when you're a member. You can swipe it, and it will activate for you. If you're not signed off on it, you won't be able to use it. I mention that because that system was built by Makerspace members. They put it together. So when you get a lot of professionals from industry, they can put together a lot of neat projects, and that was one of them that we did. Move to the next slide, please. So one of the things that we've moved on to do with all the resources we have and all the knowledge resources that we have, it was decided that we would be able to use those to further support the community and do workforce development. So with our equipment, we have engaged since 2018. The process started, and then there was a government shutdown, and then an apocalypse. And then for the last year, we've actually been engaged in the pilot program to deliver these services to the community. It was funded very generously in a one-to-one matching grant from the Appalachian Regional Commission. So $150,000 to launch these pilot programs. So our program is a 70-hour CNC training program. They also gave us, as part of the program, money to fund a mobile laboratory. And we are going to do a soft debut of that laboratory tomorrow at the Broome County Library. And with the laboratory, same concept. The idea is to take our resources to distressed schools and learning centers and show them some of the tools that we have that they might not have access to, and help them enhance their STEM education. So one of the things we've also done is partnered with Broome Tioga Workforce, and we offer a smaller version of our program to supplement their program, the OITP program, which is the Opportunity Impact Training Program. It's a great program, and it feeds into ours. Theirs is anywhere from 3 to, I think it's lasted as long as 8 weeks. And they partner with a bunch of advanced manufacturing companies in the area, and they take their students through this program to get them in the door, guaranteed interview with one of those manufacturers. So we partner with them and do that, and in turn, I'm able to speak to them, to the students, and offer them the opportunity to participate in our program, which is more extensive and also free. So the Makerspace during the pandemic was shut down. We used to have open Tuesdays. Every Tuesday, open to the public. You could stop by, meet the members, get a tour, bring in something you're having a problem with, probably get it fixed, more likely than not. And we've now shifted that to open night Fridays, 6 to 8. It used to be 6 to whenever the last person left, but these days, because of the pandemic, we have to manage it a little bit. And again, I'd like to reiterate that tomorrow, 9 a.m. to 4 p.m., we're going to have our Steamtastic event at the Broome County Library. They very generously lent out some of their parking space and some of their rooms for our event. So please stop by. And the last thing that I want to mention, we're going to be doing a series of these talks straight into the fall. And in September, everyone who participates in one of our talks, presentations, or events, who signs our attendance sheet or who we have a way to contact, will be able to win, or have the chance to win, a 3D printer. So before you leave, be sure to sign the attendance sheet.
We did have a question from through the chat, and
Sure.
the person asked, what does CNC mean?
Computer numerical control. So essentially, everything that you use without knowing it is based on this. A 3D printer, laser cutter. Essentially what it is if you had a manual mill or a manual lathe, it's the same thing. It's just controlled by a computer. You feed in the information to the computer, and it creates the object using whatever tooling is attached. The tooling is the irrelevant part.
All right, super. All right, so we're gonna transition to Jacob, or?
So yeah, so with that, the real main attraction here tonight is Jacob. He's a rock star member of our Makerspace, and I won't steal his thunder, but his plan is to send a rocket into space with a student-led team. And I think the important thing here is when I asked him why he was doing it, he gave the correct answer, more or less because he can. So with that, I'll let Jacob take over.
Yeah, sure. So I think I'm going to position the camera just a little bit.
Yeah, no, I'm using that mostly just for the microphone.
Ah, okay.
So
yeah, so
feel free to use your outside voice there.
yeah, so hopefully that works. I'm going to prop this racket up so people can see it a little bit better.
Actually, okay, so right now we'll go to the camera so that people can actually see what we're looking at. There we go. Okay.
Yeah, that should be good. I'll probably be walking back and forth
Okay.
unless you're able to man it and
Yep.
play the videos.
Yep.
There are quite a few of them sprinkled out throughout the presentation. Cool. Yeah, so if you wouldn't mind going to the
Okay,
next
so
slide.
we'll go to presentation now.
I'll try to face the camera.
There you go.
Brad, back and forth. Awesome. So my name is Jacob. I'm the founder and CEO of Aerobing. Aerobing is a space shot team at Binghamton University. We're looking to be the second student-led team in the country to send a rocket into space. And as Steven said, we want to do it because it's really cool. Honestly, it'd be really cool to be able to go around and say, hey, we put a rocket into space. With that said, yeah, what's up?
Is your rocket going to orbit?
No. So that's what we're going to is just past the Kármán line. Kármán line is generally agreed upon as the boundary between Earth and space. It's 100 kilometers up, just around 62 miles. So if you actually think about it, it's not that far. I'm sure everyone here has driven 62 miles. Just this time we're going up. So our goal is to dip our toes into space, come back down, cover our rocket, have some nice measurements that we took, and be able to say, yeah, we made it into space. With that said, we also like going around and teaching people about what we do. I can talk about rockets for hours. We do a lot of cool stuff. All the stuff we make and develop is done in-house, and we're proud of it. We love talking about it, and I think it'll be a pretty cool presentation for everybody interested in rocketry and technology. So what we're going to do today is, I just went through the mission statement a little bit more, but there's a slide after that that I'll go through in more detail. And then this presentation is split up into about 4 sections. So I'm going to go through a couple of the simulations we do. We do use a lot of math around here to predict. Safety is #1 priority, so being able to predict what we do before we do it allows us to better prepare for that. Motor development, we make our own rocket motors. So a lot of other groups like to buy their rocket motors. We thought it'd be really cool to make our own. And that comes with a whole host of problems that we've been working through and solving. Manufacturing. So this will highlight a couple of the advanced manufacturing techniques that we use. Makerspace will be included in that as well. And then I'll go through some of our rocket launches. We've taken 3 trips to the desert in the past half year to launch 4 rockets and do 1 static test. The desert's really cool. It's a great facility out there called the Friends of Amateur Rocketry Group. And they provide a nice concrete bunker and launch pad in the middle of nowhere and give us a safe place to launch our rockets. So with that, we'll go to the next slide. So this is our mission statement, fun pictures. As you can see, we like rockets. We've got big smoke plumes. We've got some research that we do. That's a microscope image on the bottom right corner of the screen. And we're in the shop all the time making our own parts. So some of the stuff we like to make are our own tubes. These are fiberglass composite tubes. Obviously, we make our own rockets. And I'll pass this around a little bit later in the presentation, but this is a cut-in-half fired rocket motor that works successfully. And we've also got Inconel Nosecone tips. If anyone's familiar with Inconel, you'll know this is a really cool material, and we were actually able to 3D print it. So more on that later. You can go to the next slide. So, simulations. Pretty much our crown jewel simulation that we have is our own developed simulation that's able to predict where the rocket's going to go in 3D space over the entire course of its flight, from launch to landing. So, this is why we need this simulation. Desert's a big place. There is a rocket out there that we judge. It is in a couple different pieces. But if you guys can spot the rocket, you guys have better eyes than I do, because I do not see a rocket there. This desert goes for miles and miles and miles, and being able to predict about where we're going to land is very important. In fact, just last time we were out in the desert, unexpectedly, we had 30-mile-per-hour sustained winds. So we launched that up, we deployed a parachute. Our rocket can drift 20 kilometers. So we need to be able to predict that, and that way we know what launch angle and in what direction to launch our rocket. We can go to the next slide. So a little bit more on why we need this simulation. In the picture on the right here, we have our launch rail. I actually should have brought a sample. I forgot to do that. But this is our launch rail. Our rocket slides on, it engages with that rail, and that way that rocket goes exactly the direction that rail is pointed. So we can rotate that rail, and we can angle it. And those numbers and those values that we get are from our simulation. So that allows us to know where that rocket's going to go, and it allows us to figure out what angles we should use. Yeah?
What desert are you launching from?
The Mojave Desert. So we are about 30 miles northeast or northwest of Edwards Air Force Base.
Okay.
So that area. The other thing that's very useful about the simulation is we can predict how high the rocket's going to go and how fast it's going to go. How fast it's going to go dictates what materials we need to use. The faster we go, the more forces act on the rocket, and that means we might need to use stronger materials or reinforce some areas of the rocket. And then, of course, we need to know that we're going to make it above the Kármán line. We're designing a rocket to go to space. If we don't have a way of predicting how high we're going, well, it's as good a luck as anyone. And then lastly, they're fighters. We launch our rockets high enough to take out an aircraft. So we need to get FAA permission to launch our rockets above a certain altitude. So this simulation is useful information. We apply for our FAA Certificate of Authorization, FAA, Federal Aviation Administration. We go to the next slide. So I wasn't sure exactly what the audience would be, so I'm going to go a little bit into the math, a little bit more into the simulations and some of the cooler stuff. Depending on what people like, if you want to know more about something, by all means ask. I can talk about rockets for hours. So just a basic idea of what forces act on a rocket. So we've got a rocket right here. As this rocket goes up, air pushes back down on it. That's called the drag force. And that force opposes its motion up. Of course, we also have gravity pulling it down. In addition, what if a wind comes from the side? It's going to want to rotate the rocket. It's going to want to translate the rocket. So if it's really windy out and this rocket isn't designed properly and a nice big gust of wind comes, it can actually cause the rocket to tilt, spin out of control, which has happened before. That's why we have the fins on the rocket. And then finally, most importantly, we've got our thrust. There's a nice big motor sitting in the aft end of the rocket here. That motor provides a thrust force opposing gravity and opposing the drag force. So if our drag force overcomes our thrust, our rocket doesn't go up.
What do you use for fuel?
So we use something called ammonium perchlorate composite propellant, and I'll get into that a little bit more later in the presentation. And of course, our rocket can go 3 directions, right? It can go, if you look at it as a grid, it can go in the X direction, the Y direction, and consider our Z direction going up. And of course, it can rotate. We call this 6 degrees of freedom. You go to the next slide. So, aerodynamics. Aerodynamics is the study of how air flows over this rocket and the different types of forces that arise and how they affect the rocket. So we do a simulation called computational fluid dynamics. It's a little bit complicated, but basically what we do is we take what's called our fluid domain. So if we drew a big box of fluid, in this case air, around this rocket, all we really care about is what happens close to the rocket. So shock waves and stuff like that happen nice and close to the rocket. As you get further away from the rocket, the effects of all those aerodynamic things like drag, lift, and shock waves kind of die out as you get further from the rocket. So we design our domain to just take into account what we care about. And that allows us to use lower power computers to actually solve our model. So that's called our domain. And then what we do is what we like to call a finite element analysis. And we break our domain up into about 1 million pieces. And when I say 1 million pieces, I actually mean 1 million pieces. This particular simulation does about 500,000 what are called elements. Take our domain, break it up into smaller chunks that are simpler to solve, and then we consider the effects of all of those overall. So this particular one, as I said, is about 500,000 elements. We've done simulations that are in excess of 1 million elements. So you can go to the next slide, and we get all cool information. Again, this is not too relevant, but this is what we use to calculate the drag forces acting on the rocket, as well as the lift and the moments. So this lets us know that our rocket will flip out of control as we go through the air, and it will also let us know that we have enough thrust to overcome the forces opposing the motion of the rocket up. You know, the next slide. And this is, of course, probably the most important thing that we get out of our simulation, altitude, how high we're going to go. So in this case, you can see this is a kind of an early version of our simulation. This is going to 140 kilometers, is much higher than we need, which is a good thing. In this case, on the right side, you've got our velocity. So this is 1,800 meters per second. That is over Mach 5, or 5 times the speed of sound. The fastest fighter jet to ever fly was just over Mach 3, the SR-71. So this rocket is kicking ass. Just a second. You go to the next slide. This is called a Monte Carlo simulation. So if we want to know about where our rocket's going to land, we do this type of simulation. And let's say we don't know, wind is very hard to predict. And wind can change where the rocket's going to land pretty drastically. So what we do is we vary the wind. So we might know the minimum wind and the maximum wind that generally occurs, and we test a bunch of different values out in between. And that way we get a distribution. So we have an idea that we have, it's most likely to land here, but we know that it could land within this radius, particular radius. And this simulation will let us know the different probabilities where we're going to land. And you can go to the next slide. And this is another version of the simulation that we run, the Monte Carlo simulation. As you can see here, these particular ellipses and circles, those show different landing areas based on the launch angle and different wind conditions. So if we launch at a steeper angle, it's going to go further, say to the left of the screen, and the wind's going to bring it back to the right. That way it lands a little bit closer to where we launched. Again, this was super important in our last trip to California. Yeah?
I'm assuming you have like a parachute that pops out.
Yep, so we use
So
what's
do
called...
you try to open it as low as you can?
Yes and no. So we have what's called a two-stage parachute deployment system. We deploy a small parachute right when it hits its max altitude, called apogee.
Okay.
This allows it to...
Drogue.
Yep, a drogue parachute, exactly. So it drops, and it allows it to slow down a little bit, but it's still going fast enough that it doesn't have time to drift 20 kilometers in a direction we don't want it to drift. Then when we get closer to the ground, say 1,000, 2,000 feet, we'll pop what's called our primary parachute. That's a much bigger parachute that'll slow the rocket down to its final descent velocity. So it's kind of a balance between how fast we want this thing to come down and how much are we willing to let it drift. And that's something we can also determine from the simulation as well. Go to the next slide. Another thing we do, as I said before, we do oh, yeah, what's up?
I just wanted to ask if you had some way to track the rocket, or can you generally see where?
Yes.
She asked,
Yeah, so
okay,
that's
just so that, pick it up on the microphone, she asked, is there a way to track the rocket?
Yep, so what we use for tracking are two basic ways. One is GPS. So we have standalone GPS modules that we put in the rocket. They downlink via ham radio bands, and we're able to track it on our iPhone or ground station, and we're able to know exactly where the rocket is at all points. The other thing we can do is use what's called an IMU, it's an inertial measurement unit. It's accelerometers and gyroscopes similar to what you have in your iPhone, and that measures the acceleration of the rocket, and you can do some fancy math on that and actually calculate how high the rocket went and how fast it went over time. The problem with the IMU is there's a decent amount of error. So GPSs are our best shot. Here's the problem though. The government controls GPSs, and they don't want people making cruise missiles. So GPSs lock out at a certain altitude and a certain velocity. It's called the COCOM limitation. And the problem is we go way above that velocity because, well, we're making a rocket. So there are special GPS units that you can get. They are very hard to get. They are very expensive
Can
to
you use
get.
the Russian satellites?
Yes, but I'd rather not.
No, or could the European ones?
Maybe. I'm assuming the Europeans and the Americans work together enough that the same.
Well,
limitations
I run and I ride a bike and I use a GPS all the time, and I can change my watch to each system. And
Yep, so we can actually
supposedly
change.
the European system is really good in cities, but I'm sure that it would be more accurate. I mean, accurate enough
Yes.
for even flying.
The other problem is how that COCOM limitation, it gets a little bit complicated, but the manufacturer is responsible for making sure the GPS unit locks out. So it's not necessarily which GPS satellite you're connecting to, it's the board on the rocket that's saying, okay, we're going too fast, we're going to cut off our connection to the GPS.
Okay.
Yep. So it's something we've been working through, we've been dealing with, and at some point we're still trying to figure it out. But we have had GPS units lock out on us. One of our recent launches went past Mach 1.5 times the speed of sound, and our GPS locked out. So we know we went at least Mach 1.5. So another simulation we do is aerodynamic heating. So when you're driving a car, it's not an issue. When you go really, really fast, air starts to rub up against the side of the rocket, and it gets really hot through friction. So when you're going 5 times the speed of sound, you can get temperatures that are hot enough to burn up our rocket. Similar to the way an asteroid re-enters the atmosphere, burns up.
Yeah.
A meteorite.
Up here at Kopernik, we call them meteorites.
Meteorite. I deal with rockets, not celestial bodies. So these are some of the simulations that we do to calculate just how hot the rocket's going to get. And these simulations are what dictate what materials we make certain parts of the rocket out of. So this is Inconel. This is a similar material that's used inside of turbine blades on jet engines, because it maintains its strength at really high temperatures. So I'll pass this around now. This is actually 3D printed. And inside of it is some electronics that we're going to use to measure the temperature at the tip. So if you wouldn't mind playing this video on the right. This is a quick just GIF of a simulation we did. And you can see the temperatures that we're getting. So we're at 300 Kelvin, close to 400 Kelvin. (500 Kelvin). So these are getting very, very hot. Hundreds and hundreds and hundreds of degrees Fahrenheit enough to burn your hand right off.
Is there anything to do with laminar flow?
A little bit. So the difference between laminar flow and turbulent flow does make a difference in, say, the skin friction. And that is something to consider. We're going so fast that we are going to end up having turbulent flow all over. So we just assume turbulent flow. But there is a difference between the two. And if it is something we could have controlled, we would have. You can go on to the next slide. So, there you go. Another cool simulation that we did is our nozzle. The nozzle is one of the most important pieces of hardware on the rocket. And depending on the actual shape of the nozzle, we can get different performance out of it. So this is the simulation to actually see the difference in shape and how much thrust we get out of it. If you wouldn't mind playing this video. So if anyone's seen the space shuttle take off, you can see these nice big bell nozzles on the bottom of it. This is a similar type of nozzle. It's a little bit hard to see. I could have made this brighter. But you can actually see right here the bell-shaped curve in the nozzle. And you can see the flow coming out of it. Oh, there we go. And this should actually look familiar if you've ever seen the space shuttle take off. This is about the shape that you get when the exhaust fully develops. And that's just that. So we were able to compare this to, say, a cone, which is a little bit easier to manufacture than a bell shape. And our difference in thrust is about 2%, which agrees with literature and also tells us that we should just go with a cone. It's a lot easier to manufacture, and the 2% difference we can make up elsewhere with easier to manufacture parts.
I ran it again. So
Oh, yeah, not a problem. And while I'm going through the presentation, if I'm explaining things that are too complicated, you want me to simplify them, by all means, just let me know. Oh, thanks.
Thanks.
Yep. Okay, so next part. We've gone through simulations. We figured out how to predict where the rocket's going to go. Now we need to design a motor to actually power this rocket, or actually a bigger rocket. This is a half-scale rocket from the one we're actually going to launch to space. So the one that's going to go to space is going to be about 14 feet tall. It's going to weigh in excess of 200 pounds. It's going to be about 8 inches in diameter. So it's going to be a big boy rocket. So, motor. If anyone's ever been in a boat where you've shot a gun or you've been on wheels and you throw something in one direction, you move the other. You shoot a bullet that way, it recoils into your shoulder. You're sitting on a boat, you throw a rock that way, you want to move back in the opposite direction. That's Newton's third law of motion. Every force has an equal and opposite reaction. So the goal of our motor is to eject a bunch of hot gas really quickly that way, or really quickly that way, and as a result, we go up. And that's called our thrust force. So we design our motors to optimize and maximize how fast and how much stuff is being shot out of the butt end of the rocket. So there are a couple different things we can do, but that transfer of momentum is what makes the rocket go up, and again, that's called our thrust force. So pictures here. On the top right is one of our successful motor tests. So you can see the exhaust coming out. That gas is traveling at about 3 times the speed of sound. This right here is just a computer-aided design model, cross-section of a rocket motor. You can go to the next slide. So I'm going to go over an overview of the parts that we have, basic parts in a solid rocket motor. So just one thing, a little bit of terminology, difference between a motor and an engine. A motor does not have any moving parts, at least in our case. An engine does, right? The car engine has moving valves, a crankshaft, pistons are going all over the place. A rocket engine uses liquid, it's got valves, it's got turbo pumps, it's got all sorts of moving parts. Our motor's nice and simple. It's a pipe with a hole at the end, packed full of propellant. So, a couple different parts. All the way on the right side of the screen, with the weird shape going through the center of it, is called our nozzle. And I talked about that a little bit earlier. The nozzle does 2 very important things. One, it directs the flow. So we want our flow to be going as opposite the direction of motion as possible. We don't want it coming out the sides, we don't want it going at an angle, we want it coming straight down. That nozzle helps direct that flow in one direction. That way we maximize our thrust up and our products down. The other thing that nozzle does, it's very important, is the shape. So that shape is called a converging diverging section. It's called the Delaval nozzle, different names for it. But what it does is it converts high pressure, high temperature gas that's moving really slowly to lower pressure, still relatively hot gas, moving really quickly, multiple times the speed of sound, hundreds and thousands of miles per hour. That conversion is what makes the rocket go up. Without that nozzle, this rocket would not go anywhere near space. So the actual shape of that nozzle, as I showed before, has a big impact on how much thrust you get out of it. And the other thing that's cool about this nozzle, it's made of graphite. Does anyone know why it's made of graphite? Same stuff in your pencils?
Doesn't burn.
Doesn't burn, exactly. It can withstand very high temperatures. Our propellant burns at mind-numbingly high temperatures, like enough to boil steel, enough to melt tungsten. Yeah. We're on the line of tungsten. Tungsten is an option, but it actually gets hot enough that tungsten becomes iffy. So we use graphite because it doesn't melt. It can burn in a very high oxygen environment, but we've actually found that these nozzles are great. We can actually reuse them. These nozzles are glued into our fiberglass tubes. The way we actually remove them is we burn the rest of the motor. The only thing that's left is the nozzle. And I have a nozzle here. I'll pass it around with the rest of the motor. This nozzle used to be inside of a rocket motor. This is burned out. So just be very gentle with it. It is cut in half. You'll see all the parts. This is a successfully fired motor, and then a separate nozzle that was fired in a different rocket and then burned out. So on to the other parts. Of course, we also have our propellant. In this case, this is a half section of the rocket motor that's already been fired. So our propellant will be right smack in the middle. Of course, all that propellant is gone because we fired the motor. At the left end, we have what's called our bulkhead. Our bulkhead is like a wine cork. It keeps all the pressure in that side, so all the gas goes out the nozzle. All it is a pressure cap. And then we also have the outside, which is a fiberglass tube. The fiberglass are a bunch of little fibers of glass woven into a mat, wrapped around what's called mandrel, in this case just a tube, and then we coat it in epoxy resin. So the combination of epoxy resin, glue, and fiberglass makes a super strong, super tough material. So its cousin, carbon fiber, similar material, is used. NASA loves carbon fiber. They use it all the time. We've opted for fiberglass because it's strong enough for what we need, although not as strong as carbon fiber, but much cheaper. So I'll also pass this around. This tube right here needs to be very dimensionally accurate, needs to be very strong, and needs to be able to hold a lot of pressure. Anyone can squeeze this and break it, I'll give you $20. And that's one of the weaker tubes we've made. We've actually strengthened them more. So that's our tube. Now, finally, is one of the most important parts of this rocket motor. It's called our liner. The liner is, if you have a hot cup of coffee and you want to keep the coffee hot, you put an insulator around it. Our liner is the insulator for our rocket motor. It keeps the heat in and it also prevents the heat from getting to the fiberglass, weakening it. Yep. So remember, our propellant burns at thousands of degrees Fahrenheit. This fiberglass can start to weaken at only a couple hundred degrees Fahrenheit. I heard a little crack there. No, that still looks like a tube to me.
$1.50.
So this liner works as an insulator. It prevents the heat from weakening the fiberglass and causing overall failure of the motor. And it does that doing two things. If you wouldn't mind going back a slide. Or, sorry, forward a slide. Yeah, there we go. So this liner material is made of a material that's very bad at transferring heat. It's called an insulator. It has a very low, what's called thermal conductivity. It also has a feature of it where it likes to ablate. Ablation is where it actually sacrificially burns. When it burns, it absorbs heat, injects some gas. So instead of transferring that heat's absorbed and then ejected. So actually that's not these particular nozzles, but NASA does have nozzles that work on similar principle. So those are the basic parts of the motor, and all those parts are included and highlighted in that motor that's been passed around as well. So hopefully, if anyone wants to take a look at it in closer detail after the presentation, by all means, I'll leave it out here. You go on to the next slide. So now we'll talk a little bit more about our propellant. So we use something called EPCP, ammonium perchlorate composite propellant. Essentially, it's glue with an oxidizer mixed into it. So when you light wood on fire, wood is your fuel, and then oxygen from the surrounding air is your oxidizer. In this case, it's all mixed together in one nice compact package, which means if you do light it on fire, putting water on it isn't going to suffocate it, it isn't going to put it out. So it is made of something called polyurethane rubber. HTPB stands for hydroxyl terminated polybutadiene. It is basically, as I said, it's glue. Okay, you can glue things together with it. You can make rubber. People cast it into nice, cool shapes. We like to cast it into rocket propellant. This particular rocket propellant was actually a similar version to it, used a couple of different chemicals, but a very similar formulation was used on the solid rocket boosters of the Space Shuttle, and I believe is also being used on SLS as well. Ammonium perchlorate is our oxidizer. I don't need to get too much into the chemistry of it, but we use a couple of different sizes to increase our packing factors. So we want to pack as much ammonium perchlorate in there as possible. So ammonium perchlorate is analogous to the oxygen in the air when you're burning wood. We also add other additives to it that aren't too important, but they do make it a little bit more workable, and they change our burning characteristics a little bit. If you have any questions on the additives, I'd be happy to answer them after the presentation. And then stability. So one of the nice things about APCP, it's actually kind of hard to light on fire, so it's really safe. I mean that. I've kept a piece of it in my car for the last 10 months. It's fine. It's glue. We've actually impact tested it by shooting it with a shotgun. Doesn't care. It rips into a bunch of pieces just like a piece of plastic would if you shoot it with a shotgun. It burns very bright. So if anyone's ever lit magnesium on fire, magnesium burns a brilliant, white, blinding light. This does the same thing, but just a little bit more yellow. On the right-hand side of the screen, we have a microscope image of our propellant. You can see nice big chunks of ammonium perchlorate, and then the HDPB binder, the polyurethane binder in the middle, holding everything together. Go on to the next slide. So this is just a little bit more on our propellant. We're at Binghamton University. We've got really powerful, fancy microscopes we like to use. So on the right here, that is a picture of our 5-micron aluminum powder. 5 microns is ridiculously small. That is less than 1/1000th of an inch. It's multiple times thinner than a human hair. This particular, what we use this for is to make sure that our particles are as big as they say they are. Oh, actually, my mistake. This is our 30-micron aluminum powder, not our 5-micron aluminum powder. Just over 1/1000th of an inch. So we use this to make sure when we order aluminum powder and they say it's 30 microns, we know it's actually 30 microns. And you can see here, just 32 microns. For those who aren't familiar, micron is 1/1,000,000th of an inch. Of a meter, sorry. And then on our left, we've got another microscope image of our propellant. So you can see the chunks of ammonium perchlorate, and then all the glue in the middle holding everything together. Go on to the next slide. So, we've done our motors, we built our motor. This is what happens when we don't do anything right. You can play this video. If you have sound to it, so that's what happens when a motor doesn't work. Oh, don't worry, it'll keep burning. Remember that thing I said about the nozzle directly slow? Yeah, you can see it. It's coming out of place and soon to be coming out of it. So this also, as cool as this is, it does also bring up another interesting
Actually,
point.
looks pretty hot.
It's very hot. It's very, very hot. We had aluminum plate under that, melted it. And it was sitting a couple inches away from it too. And it wasn't directly in its path, it was kind of just next to it. Yeah, so it gets hot, really hot. So one of the nice things about APCP is it's not an explosive. Some people kind of confuse the two together. It's very much not an explosive. If you notice, it took 30 seconds to burn. If that was an explosive, well, it would have exploded. So at ambient pressures, our propellant burns really slowly. But once you start to raise the pressure of it, that's when it burns really quickly. So that's the key aspect of our propellant. Open air, it burns like anything else. Bright, hot, but not particularly exciting. When you confine it and let the pressure go up, that's when it goes into a runaway reaction. And pressure goes up, burn rate goes up. Now as pressure goes up even more, you get this runaway overpressurization, and your motor blows up or burns through or something like that. So this is a good case of what not to do. And just a note, we also did this with the Town of Binghamton Fire Department. So they had the fire chief was on site. If there was a fire, they'd be ready to put it out. And this was done literally on snow. We have our nice big steel test stand that's bolted into the ground. So there's no worry of this escaping, no worry of it causing any fires and harming anybody. We're way back there, and if you notice, there was a cinder block wall separating us and the motor. And then we also have a deflector plate, just in case sometimes one of our failures is our nozzle comes loose, shoots out of the rocket like a rocket, and hits that deflector plate, which shatters into a million pieces away from where anybody's standing. So our operations are actually quite safe. We've never had any incidents in which we've ever worried about someone getting hurt. No, there's no hoping. We make sure it's safe. So we'll go on to the next slide. This is what a successful motor is supposed to look like. This particular motor is not the one I'm passing around, but it does look good. When that motor worked, it looks similar to this. So you can play this video too. That was a couple 100 pounds of thrust over the course of 5 or 6 or 7 seconds. About 7 pounds of propellant burned in that really short amount of time. So that's what happens when you have a good motor, a successful motor, and it actually raises the pressure, doesn't explode. It burns really quickly, it burns beautifully, produces a nice amount of thrust. So that's what our motors are supposed to look like. We go on to the next slide. So now I'm going to highlight some of the manufacturing processes that we use. So one thing that we like to joke about is we're not NASA. NASA spends like 6 months making a nozzle. We make a nozzle in a day at cheaper materials because, well, we're not NASA, we don't have a ton of money. And we've got to improvise and be creative with our limited manufacturing and our limited resources. So we like to make our parts cheap and functional. We use what we have, and one man's trash is another man's treasure. I've been known for dumpster diving my entire life. There are perfectly good scraps of aluminum sitting in a dumpster. I'm taking them and turning them into rocket parts. So that's what we like to do here at Aerobic. We go into the next slide. So first process we'd love to use is additive manufacturing, 3D printing. We use all different types of 3D printing processes. First and foremost is fused deposition modeling. You might also hear it be called FFF, which is fused filament fabrication. So that's where you take basically squirt out a line of filament, plastic. You keep doing that until you've got a 2D layer. You move up a little bit, and you do that again on the next layer. That way you can build up a 3D part. All of these parts in the left-hand picture were printed with FDM, except for those white PVC tubes. Also on the right side of the screen, we print our alignment jigs for our fins. So we use 4 fins on our rocket, and we want to make sure they are aligned perfectly. We do that with 3D printed jigs that hold our fins in place while we glue them. We also like to print things out of resin. Steve mentioned this. Steve mentioned this a little bit earlier. The Makerspace has what's called a DLP, or a laser printer, and that basically shines a laser under a bed of photosensitive resin. It likes to cure under the sun, essentially. So that little laser causes little dots and lines of resin to cure, and then it'll lift up a little bit, it'll do the next layer, and that way you can actually print parts out of liquid resin. The advantage of the liquid resin printing is it's very accurate. You get really, really fine features printed.
Is it just one laser, or
Depends on the machine. So there are a couple different flavors of it. Some of them have one laser, some of them have multiple lasers that raster in different parts of the bed, that way it goes faster.
Oh, I was thinking that you had to converge them or something.
No, so
Okay.
nowadays our lasers are powerful enough that there's no need for it. The other way you can do it is really interesting. Let's say you have an ultraviolet light hidden beneath the screen, and this entire screen, each pixel is like a light switch. When a pixel goes on, it lets some light through. When a pixel goes off, it blocks light coming through. That way, you can have what's basically an ultraviolet projector, and you can do one entire 2D layer at a time. So it's a very fast way of printing. You can actually get one on Amazon for $200-300. I just ordered one the other day. They're great. And we have one that we use for Aerobing all the time. So it's called MSLA, masked stereolithography. It's the whole point is basically an LCD screen that allows light to come through. And then metal. So I think I passed this around before. Markforged Metal X is an awesome printer. What that basically is, it's an FDM printer, but instead of using plastic filament, it's plastic filament with a lot of fine metal powder mixed into it. So you print with the plastic, then you dissolve the plastic in a chemical bath, and then you sinter the part in a really hot oven. That kind of melts it all together into a solid metal part. So you get rid of the plastic, and then you melt it together, and it actually holds the part. And the interesting thing is this part, when you print it in plastic, is 18% bigger volumetrically than this part, because it shrinks when you heat it up. Go on to the next slide. So this is a little bit of, this is the Markforged Metal X printer in these left 2 pictures. That's the printer itself. It's basically just a regular FDM printer, just costs more. And then on the right side, the middle picture, left side, is the wash station. That's a chemical bath that dissolves. It's called debinding, dissolves all the plastic inside. And then that final step is a sintering oven. So it's an inert environment to make sure there's no oxygen that can react with the metal. It heats it up really hot, and it does something called sintering, and it also burns out. There might be some little pieces of plastic left. It's so hot that the plastic actually vaporizes and evacuates. And you're left with a solid metal part that's basically 99% as dense as a regular cast part. So this is a really cool process, and it's allowed us to do really interesting things with really exotic materials. So Inconel, for example, is super hard to machine conventionally. It would be extremely expensive, it would take forever, and it's not something we have the resource nor the time to do. 3D printing's allowed us to get a turnaround time in a couple of days. And the other thing that's really cool is, if you noticed, it's hollow. It does a couple of things for us. One, that allows us to put electronics inside to measure. So if this was solid, obviously we couldn't put electronics to measure the temperature at the tip inside of it. The other thing we can do, and you might be laughing at why we do this, next time we launch a rocket, this will be filled with lead. Yes, it will be filled with lead. So what that does is two things. One, this is here to resist temperature. But we want it to be hollow, but we also want it to be heavy. Because when this is heavy, it makes the rocket more stable. So it actually allows us to optimize our weight. We take our heat-resistant material on the outside, and on the inside we put a really heavy material like lead. It's literally a composite metal nozzle, a composite metal Nosecone tip. It seems a little bit counterintuitive, but it's actually a cool idea that we're hoping to test out, and we hope it works. And again, couldn't do it without 3D printing. And if anyone wants to try CNC machining this, be my guest. I don't even know if it's possible. We can go on to the next slide. So, as much as we love 3D printing, CNC machining has also been a big help for us. So as it came up before, CNC machining, computer numerical control. It's a computer-controlled tool. So you've got a spinning, looks like a drill bit on a tool head that removes metal, and then it's positioned in up and side to side is controlled by a computer. That way you can make really complex shapes inside of things. So there's no way a human operator would ever be able to make those types of curves in a shape like that. Plus, you can sit around while the computer does the work for you. So this takes 40 minutes to machine. I can sit down and get a cup of coffee while the machine's working its tail off. It also allows us to make, again, these complex curves that you couldn't do by hand. So this right here is what we call an aluminum bulkhead. This was the result of a lesson learned on a past launch. We crash landed in the desert. Rocket wasn't very strong, and we had electronics sandwiched between two plates that failed, and all of our electronics broke. So we said, okay, we need those plates that are protecting the electronics to be a little bit stronger. So we're going to make them out of aluminum. But aluminum, solid sheet of aluminum, would be heavier than we wanted. So we use CNC machining to mill out all of those pockets. So we have a strong bulkhead, but it's also very light. We haven't tested if this works. Well, we've tested it in flight. We haven't tested if crash landing affects the electronics yet. But it should be better. On the right here, we have what are called fin tips. So it's actually a little bit hard to see from this picture. I could have used a little bit of a better picture. But everyone knows the Windows cursor, right? It's a little arrow, basically. Yeah, imagine that, just long. That's what we put on the tips of our fins, and I don't have it here, because in addition to the Nosecone tip getting really hot, our fin tips also get really hot. So instead of making those out of plastic or fiberglass, which is weak, it fails at low temperatures, we make them out of steel. And then all the way on the right, that is an 8-inch diameter, well actually a 9-inch diameter by 1 foot tall chunk of graphite. That is a 60-pound chunk of graphite, and that's what we make our big nozzles out of for our 8-inch final diameter rocket. So as you've seen in that thing that I just passed around, those are 2-inch nozzles. Those are tiny, right? We can do those pretty easily ourselves on a conventional lathe. That does not fit on any lathe that we have. So we actually had to go and CNC machine the inside parts. That's what we'd call our roughing operation. It's basically a rough cut that removes the bulk of the material, but doesn't leave a very smooth finish on the inside. So we're going to go in after and smooth that out. But again, CNC machining couldn't do that without the computer numerical control aspect of it. Go on to the next slide. So our tubes. So we've gone through a couple of our manufacturing processes. Now I'd like to go through a couple of the actual parts themselves. So our tubes are very important. They form the pressure vessel for our rocket motor, as well as an airframe for our rocket. So it needs to be able to withstand all the aerodynamic forces, pressure, and the decent temperature. So we found a really cheap way to make tubes. PVC mandrels. You walk into Lowe's, Home Depot, you can buy for relatively cheap a PVC tube that is 4.5 inches in diameter, 5 feet long, and it just so happens that that's a perfect half-scale rocket for us. Turns out also that PVC pipe is relatively dimensionally accurate. It's actually relatively precise, at least for our purposes. So we take our PVC, called a mantle, we actually apply turtle wax to it. Anyone who's worked on their car, I'm sure is familiar with turtle wax, and that becomes a release agent. So we can actually slide these tubes off after we make them. So that tube I passed around before was also made on just a smaller PVC mandrel. And you can see here on the left, it's a bunch of underclassmen that we're training up and teaching how to make our tubes. Wouldn't mind going to the next slide. We also have really big PVC tubes for making our final rocket. That's a 5-foot tall tube, about 8.65 inches in diameter. That black tube is the mandrel. That's a Schedule 80 PVC tube. And on the left is our PVC tube. On the right here is our 10-foot tall versions of the PVC tube. We have not made a fiberglass tube on those yet. But if you notice, right smack in the middle, there's a $20 bill for scale. Those are really big tubes. I think I could fit you in one of those. I might be able to fit me in one of them.
I don't think he's actually suggesting.
No.
Don't record it, so.
They're just big tubes. Go on to the next slide. So, our nose cone. I'll pass this guy around. This is a very unfinished early version of the nose cone that we made. At the end of the day, if we had a flat top here, drag would interact with that, and it would oppose the motion of the rocket even more. So we have this nice aerodynamic shape that cuts through the air, and that's why we have a nose cone. Our nose cone needs to be relatively strong. It might house electronics. It might also have a parachute on the inside, and of course, it is right in contact with all the aerodynamic forces that are acting on it. Yes?
Can you send up a camera?
Yes. We have had limited success with the cameras we've sent up so far, but the next time we send one up, I'm confident we'll get some cool video back. So, hopefully we'll do another presentation. I'll be able to show that off next time. But the way these are made is, again, 3D printing. We 3D print basically the entire inside of the nose cone, then we wrap it with fiberglass. In order to get the fiberglass to conform to this shape, we vacuum bag it. So we actually put this in a special type of bag. We make the bag around it. We suck out all the air. And remember, the atmosphere is always pushing down with 14.7 pounds every little square inch of this, which is actually really strong. So if we suck all the air out of it, we now let the atmosphere do the work, and it pushes the fiberglass into the printed mandrel, and it conforms to the shape. So this is really strong, and this is actually a weaker version that we made, because we usually fiberglass the inside as well, and this one is not fiberglass on the inside. Just a note, when I'm passing this around, the top part is a little bit rough, so I avoid touching that. And of course, on the final nose cones that we make, we sand them, we paint them, we make them look really pretty. Go on to the next slide. Microspheres. So that liner that's inside of that rocket motor that I passed around is made out of a special material that we like to call microspheres. They are tiny little glass bubbles full of air. They're very small. It's really fine powder. It's like flour. And we mix that with polyester resin, again, glue. Polyester resin is super cheap, burns nicely. When we add the microspheres, we decrease its weight, and we decrease its thermal conductivity. So we actually make it a better insulator, and we make it really light. So it's actually an ideal material for us to make any type of insulative parts. So liner, our bulkheads are actually made out of it. It's relatively strong, and again, super lightweight. So again, we make our liners, our bulkheads, and we actually put insulation around the nozzle, made of this material as well. Go on to the next slide. And of course, our nozzles, I went over this before. One thing I'd like to highlight here is on the bottom right corner, that's actually an X-ray of our nozzle. So we also, again, Binghamton University does give us access to an X-ray machine. It's very cool that we can be able to see into the rocket nozzle without having to cut our motors in half. This allows us to do a post-mortem. It also allows us to look at the inside of our motors before we fire them. And that gives us something to compare to. So something that's actually really interesting that you can see here, I'll try to point to it. This part right here, this dark part, that's actually slag buildup. So if we don't burn efficiently, we have aluminum powder inside of our propellant. And if that doesn't actually burn, it likes to build up on the inside of our nozzle. That causes what's called the throat of our nozzle to get smaller. And when our throat gets smaller, the pressure in the motor can go up. And as you've seen before, if our pressure gets a little too high, burn rate goes up, we get a runaway overpressurization, and that phenomenon right there can actually cause our motor to catastrophically fail and blow up. Cool, but not cool if you're trying to make a motor that works. So this is actually a very important thing that we like to look at both before and after flight or firing, just to make sure that we burned our aluminum powder efficiently. Go on to the next slide. So more on the nozzles. This is a picture from before. Big nozzle. These are the chunks of graphite that I'm talking about. In the rightmost picture, that is a jumbo glue stick sitting on that chunk of graphite. It's about 300 pounds of graphite, at 360 pounds of graphite, about 70,000 pencils based on conservative estimates. A lot of graphite. One thing that's nice about graphite, it's relatively easy to machine. It does create a lot of dust, but vacuums and masks are a good way to combat that. We are looking into composite nozzles, so we can either use that microsphere mixture to make the lower stress parts of the nozzle, and then only make the throat region, which is the high stress part of the nozzle, out of our graphite. So we also might use something called phenolic, which is similar to, actually this is not quite phenolic, but similar. So you can get phenolic, which is basically sheets of cardboard or fiberglass, and then what's called a thermoset resin pressed together. So FDM is what's called a thermopolymer or thermoplastic. You can melt it, you can soften it, it'll solidify when it cools down. A thermoset, once it reacts, that's it. You heat it up, it's not going to melt. You heat it up, it's going to burn, which is one of the reasons we actually want to use it, because we don't want our nozzle to melt. We'd rather it burn a little bit than melt. So that is something that other college teams have done, something I'm sure NASA has looked into, and something we might look into in the future as well. Go on to the next slide. Liners, so I went over this before. Our liners give us something to cast our propellant into, and they insulate the fiberglass body tube from the hot propellant gases. We go on to the next slide. Now, most exciting part, rocket launches, right? Why do we do all this stuff? At the end of the day, we want to launch rockets. So on the right here, on the left, right side of the screen, left picture, that is the Friends of Amateur Rocketry site in Mojave Desert. It's a gorgeous site. They have tons of launch rails and launch racks. They have concrete bunkers. Right smack in the middle there is their underground concrete bunker. If you want to go and blow stuff up, it's a perfectly safe place to do it. It's got miles of open desert, so we can launch our rocket, come down like a rocket, and not worry about taking out a house. Ford has been there. If anyone's familiar with the Mach-E commercial, where they launched a sugar rocket and then drove a Mustang out of it, they did that at that site. The Mythbusters were also around that area. They did their JATO car there as well. It's a dry lake bed, just past that big tower in the middle, and that's where they launched their JATO car. And on the right side, again, I said you can basically do anything there. If anyone's familiar with BPS Space on YouTube, and what's her name, Zyla Foxland on YouTube, they were both there. They launched a Christmas tree last Christmas, and we got to see it in person, which was super cool. So, Aerobing in numbers since December. Since December 2021, we've taken 3 trips to the Friends of Amateur Rocketry site in the desert, done 1 static motor test, and we've launched 4 rockets, the highest of which is past the sound barrier and gone over 8,000 feet. So, not quite space, but we're getting there. Someone have a question?
I was just gonna ask how high
Oh,
you
yeah.
went.
How high? Yes. So,
You said 8,000 feet.
yep, we went 8,000 feet and 5,000 feet. And I'll go over each one of those rockets and show you videos of the launches in the next coming slides.
How do you travel with the rockets to these sites?
So,
Repeat the question, please.
oh yeah, so the question was, how do we get the rockets to the launch site? So, short answer is, a lot of the hardware that we actually make, if it's small enough, we can bring it through the TSA. We'd like not to, but we don't bring our propellant on person. We have our chemicals shipped direct to the launch site, and we make our propellant at the site under the supervision of experts over there. In terms of the larger components, those are shipped, or we make them out in California. So one of the really nice things about PVC tubes, they're standardized. We can go into a Lowe's in New York, buy a 4-inch nominal PVC tube. You can go to California and buy that same exact tube. So we were actually able to do that for our first trip. We made our tube out in California. All we did was we shipped our fiberglass and our resin, and we bought the tube out there. And again, in terms of propellant, none of that gets shipped. That's all made direct and at the site under their supervision. This past trip, we actually built up, let's see, it was 1 foot by 1 foot by 6 feet long wooden crates. We shipped those out full of our rockets. Go on to the next slide. So, 3 trips. I'm going to go over each trip, show you some pictures and some videos, tell you what we did. So, first time we went out to FAR, you can see we launched a nice big half-scale rocket. We also did a static motor test. So, this is a 4-inch diameter rocket. Oh, actually, that's a 3-inch diameter, sorry. Rocket motor. So that fits into that tube back there that I passed around. It's got what we call 2 cores. So each one of those separations right there contains a nice chunk of propellant. And we were able to launch our first half-scale rocket. So that was a rocket that, of course, had the same nose cone, was about this size. We learned that the sound barrier is not an easy thing to pass. So we launched this particular rocket. We didn't do a very good job attaching our fins. One of the fins broke off right when we got near the sound barrier. Then it flipped, then another fin broke off, the rest of the fins broke off, the motor ended up all the way there, The rocket actually broke in half. Our nose cone came down in pieces. So yeah, a rocket came down in a bunch of pieces. So we learned the hard way that the sound barrier is a rough time for a rocket. But the nice thing is that informed our design for our next trip.
Is that, when NASA talks about like rockets that go through max Q,
Yep, that's exactly right. Yep, that's exactly, pretty much at around max Q, our fin broke off, and then our rocket broke. We like to say we bounced off the sound barrier. We didn't quite get through it, but we neared it. So that's our rocket on the launch rail there. And this first trip was really us going out there and seeing, all right, what's it all about? Because there's a lot of logistics there. We're flying out there, we've got things that are shipped out there, we've got things that need to arrive before we do, we've got to pick things up from different locations, bring them all around, and it becomes a whole big logistics problem. And this trip gave us a good chance to iron out a lot of those logistics before we start bringing more team members out. We can go on to the next slide. So this is a video, actually 2 videos. So I told you we did a launch and static test. This is our launch on the left. So it goes up nice and straight, and you see it does a nice corkscrew at the end. So that's when one of those fins came off and the rocket decided to tumble like that. And then on the right side, we've got our static motor test. That means we fire off the rocket motor, bolt it onto the ground. We don't want it to go anywhere, we just want to fire it off and make sure it works on the ground before we stuff it in a rocket and shoot it up. They can play that video. So you can actually, I don't know if anyone caught that, just at the beginning, you're actually able to see shock diamonds in the exhaust. It's super cool. Not necessarily the best sign, but it is cool. Those shock diamonds are real good seconds. After around 2 seconds. Cool. Go on to the next slide. So, second trip. This time around, we didn't do any static tests. We decided to launch 2 half-scale rockets. So again, rockets of this size, but with varying amounts of propellant. One of them was basically filled to the brim with propellant. So filled to about here, about 25 pounds of propellant. It's a lot of propellant. And the other one had a much smaller motor. And this was just to be able to launch 2 rockets, test our systems in the sky, but not have to make 50 pounds of propellant. So this was where we actually had our most successful launches. We had our Cat 4 and our Cat 6, what we like to call them. The reason Taylor is Cat 6 is it was originally designated Cat 5, but we're busy out there, we're doing a lot of things. We accidentally wrote 6 instead of 5 on the rocket. So Cat 5 didn't happen. It's just now the Cat 6. So our post-flight analysis, our Cat 4 rocket went up to 8,000 feet. It went past around Mach 1.5, which is over 1,100 miles per hour, just to give you a scale at just how fast that is. We were also able to bring an additional team member out, which is nice, and practice our logistics more, checklists, safety precautions, all of that stuff. When it's launch day, things are hectic, things are crazy. Having those checklists, having those launch procedures, and being able to practice them is a big help and very important to our operations. So, leftmost picture, that is really crappy quality. I don't know why it came out so bad, but that is me cranking up the launch rail. So we're able to, it's on a little hydraulic thing, or a screw jack, and we basically bring it all the way down, slide our rocket on, and then crank it back up. In the middle there, that's Jeremy Gendler, Chief Engineer. He's arming the electronics of our Cat 6. And then in our rightmost picture, that's our muscle, it's Chatty 6'6". He's doing some sanding and preparation on the fins. So you can go on to the next slide. So on our left here is our launch of the Cat 4.
Oh.
You can go on to the next video.
We got smoke.
That was the Cat 6. So before we go on to the next slide, just 2 notes on these videos. This leftmost video, if you notice how the rocket turned,
Yeah.
that was something we needed to improve on, that we improved on our third trip. There was a little bit of crud inside the rail, and I wish I brought a demonstration for this, but the way it works, we have these little buttons that engage with the rail. And if there's any type of crud inside the rail, those buttons will get caught on the rail. In this particular case, there was crud on the rail, the buttons got caught, the rocket kept going up, but now it had no guidance. So it decided to turn a little bit, because why not? A good thing we're in the desert. It landed a couple miles away. It was about 15 degrees off towards the north in that particular frame of reference. But because we had GPS, we were able to find it and recover it. I'll show you pictures after. Other note, parachutes didn't deploy in that one. That one came down like a rocket. And some interesting things about Inconel. On the right, and this was the lower powered of the two rockets. On the right side, that was our Cat 6. I'm going to show, before I actually go into this one, we'll show the video on the next slide. So if you notice, that was supposed to be like a 5-6 second motor burn, and it only burned for about a second. It did deploy its parachute, but it deployed it on the way up, which is not exactly what we want. So what happened here is, remember that bulkhead that I talked about before? It's like the wine cork. Well, that decided to come off, to come loose. So our motor immediately put itself out, it depressurized, so it stopped burning, and then that bulkhead decided to shoot through the entire body of the rocket. So our bulkhead is generally about here. We've got electronics here, parachute here, nose cone here, and that bulkhead shredded literally everything in its path. Came out like a bullet. So that's why our parachute deployed. And that rocket also somehow was stable enough that even without a nose cone, it went up and came down like a lawn dart. And I'll show you on the next couple slides. Pretty much a video again. So you see that rocket? It keeps going up, which is great. Remember, this is a more powerful rocket. So this was the first rocket I showed that veered off. Well, it didn't deploy its parachute, so you can see it ripped itself apart on the right. This is the Inconel nose cone tip. That was buried 2 feet underground. That's a steel rod. Yeah. But the amazing thing is, look how the Inconel survived. With a little bit of finishing and touching up, that's a flyable nose cone tip. Inconel is amazing. I'm just going to say that. And you can see, of course, that rocket shredded itself. And you can go on to the next slide. We also recovered the Cat 6. These are pieces of the nose cone. As you can see, that is a piece of the electronic system in the middle, and that's our rocket after it came back down. Remember, this was a 7-foot tall rocket with like a 2-foot nose cone. Not even. With a lot of rocking in the drum there. So, we learned a lot of lessons on this trip, and we went out a third time. You can go on to the next slide. So, our FAR trip 3, this time we were able to bring another 2 team members out there. And this was a good test of our logistics. It turns out California has a lot of wind. There's a reason there are wind farms all over the place. We didn't realize that. We had 30-mile-per-hour sustained winds the entire time we were working and when we launched. Not something I'd ever experienced before. It was rather crazy.
What time of year was it?
3 weeks ago? Yeah.
Yeah, I used to go out for work, and I used to think my rental cars had a problem with steering because
Yep.
I'd be going in one direction.
I remember the first 2 times we went out there, I made the comment, I said, why are there so many wind farms? There's no wind. Just put solar panels. Well, those wind farms were working when we were there. They were spinning. So this time we launched another 2 rockets. This time we actually shrunk one of our rockets down just a little bit, just to test different scale systems. We went to about a 1/3 scale. We designated the Cat 8 in honor of a friend of ours, Andrew Desiderio. He sadly passed away a year ago. So this was a rocket in tribute to him. So our Cat 8 post-flight analysis, it did launch. It wasn't terribly stable off the launch rail. 1 due to wind, 2 due to a motor failure that we had. But it did go past 5,000 feet. Fortunately, it didn't go very fast, only about 450 miles per hour max velocity. And again, we were able to bring out 14 members. So on the left here, you can see myself and a friend of mine, Eli. He's cranking up the rail as I did in the last picture. On the middle picture here, that's Kira. She's working with the electronic systems and Jeremy to pack our parachutes. And then all the way on the right, we've got our Cat 5 Taylor. So remember that rocket that impaled itself into the ground? Well, it still actually had most of its propellant inside. So we actually brought out a repair kit, and we were able to refurbish it back in the desert. So unfortunately, we haven't launched that rocket yet, but next time we go out there, we will. And then Kira, in that picture, is holding the Cat 7 Lippmann, which is a bigger rocket that we also unfortunately didn't have the chance to launch. Get more into that later. But that is dedicated to my science teacher, late science teacher Shelley Lippmann, who died of cancer a while back. Best science teacher I've ever had. If anyone's seen October Sky, she was Mrs. Riley.
Yeah.
So she was awesome. But on the next slide, I'll show some pictures, some videos and pictures. So that's our Cat 8 Andrew. Again, that's still a tall rocket, the middle of the rocket, full of about 8 pounds of propellant. And on the right side of the screen, we've got our video of it. associated with wind. So that rocket was a little bit unstable off the pad, again, due to wind and some other issues. If you're interested, I'd be happy to talk about those issues after the presentation. Nice thing about this rocket was the first time we actually successfully deployed our parachute. It came down, we recovered it, and we found some interesting things about it. But we were very happy to recover a rocket and deploy our parachute. So that was a big milestone for us. You can go to the next slide. So, what's next? So, we had 3 launches scheduled for our past trip to FAR, but we only got to launch 1. We had last-minute electronic issues, so we decided to push off the launches of the 2 bigger of the rockets, the one on the left and the right, the Cat 5 Taylor and the Cat 7 Lippmann. We had GPS failures, and without those GPS units at 30-mile-per-hour wind, we're not going to ever find those rockets without them. So we decided to scrub those launches. We'll come back mid-summer, and we're going to improve our electronics, and we're going to launch those babies up. Eventually, once we launch those 2 guys, the next rocket that we're going to launch is a 2/3 scale rocket. So that is 75 pounds of propellant, 6 inches in diameter, 6.5 inches in diameter, and around 10 feet tall, so through this ceiling. So that is a big rocket that we're going to be launching. We hope to start building at the end of summer, launching in the fall. And then if that goes well, we're going to be doing our space shot. We're going to be attempting to be the 2nd team in the country to put a rocket in space.
So are you looking at next year for that?
No, I hope to do it this year. We like to pull a SpaceX. We make really short, unreasonable timelines. We do the best we can to make those timelines. We get a lot of progress done. Then we say, okay, let's do that again. So that's what we like to do. So our timelines are ever changing and ever adapting to our current research and our development. But
Now,
we've made a ton of progress in the past 2 years.
when you do your space launch, do you plan on sending like a little mouse into space and back, or
Liquefy it.
Probably my MIT
or an
rejection
insect
letters.
or something?
I'll put that in there.
Well, could you do it though?
We could. If you can provide a mouse, you might be able to make something happen. Although I don't know if I want to do that to a mouse.
You have a sense of how many Gs
Yep.
that thing's pulling?
So let's see, 20 or 30 Gs off the launch pad, which is our max. So no human would be able to survive that. That's actually a big
or a
difference
mouse.
between what?
Or a mouse.
Or a mouse, yeah. So that's a big difference between these rackets and something like this. This needs to be able to carry people. So maybe 2, 3, 4 Gs max on this guy, I believe. These guys, no person would be able to survive or be comfortable surviving. And I think that is the last slide I had in here. Does anybody have any questions, anything you want to know? I love talking about rockets. Here as long as you want.
We have a question from the chat, the YouTube chat, is how expensive is each launch on average?
So the interesting thing is right now our dominant cost is our travel expenses. Flights, shipping, motel, car rental, launch site fees, all that stuff dwarfs our current launches because we use a relatively small amount of propellant. We bought a nice large large roll of fiberglass that's lasted us for multiple rockets, and we've gotten our processes and manufacturing down to really cheap. So building a rocket could literally cost us a couple $100, while traveling out cost us thousands. Once we get a little bit bigger, our propellant will start to cost more than our travel expenses. But for right now, our past trips, around $5,000 total.
Okay.
Something else I'll pass around. This is what we make our fins out of. This is called G10. It's layers of fiberglass and resin pressed together. This is also what they make circuit boards out of. So again, if you can break that, there's another 20 bucks out there.
Yeah. Question? Yeah, go ahead.
Oh yeah, hold on. I think you were first.
Oh, sorry, yeah, I just was curious, I know you mentioned you have an aggressive timeline and it's always adapting. How long does it take when you're on site to, manufacture some of the necessary parts and mix the propellant and, I assume you build time in for all that?
Yep, so we usually take 2 days at the launch site, 1 day to get everything ready, and then 1 day to launch.
Okay.
And then we have a backup day right in the middle of that. So our trips go from, right now they've gone from Wednesday to Sunday essentially. So we travel Wednesday, we make our propellant Thursday, Friday is a backup day, and hopefully if we get our stuff done on Thursday, it's an off day, then Saturday's launch day.
Thank
Yep.
you.
No problem.
So I noticed that you shelved some of the launches for later. But those already have the propellant mixed, and one of them was even sitting from further back. Does the propellant denature, or?
So very good question. So generally, it's actually very stable. It might lose a little bit of performance. There are a couple things. One, it can absorb a little bit of moisture, so you don't want that. The other problem is when you mix your oxidizer and your fuel together, well, it's not going to start to burn, but it can start to react very, very slowly. And that'll cause the propellant not to be as reactive and as efficient as it will be. So if you are planning to store it very long term, there actually are things you can add to preserve its shelf life. But for a couple months, we're not too worried about it.
Okay.
Yep.
Well, how do you actually ignite? Yeah.
So what we do is we take, so one of the things we like to do is we make sure we ignite our propellant all the way from the rear. That way it burns all the way from the rear down to our nozzle. That ensures that we get a constant burn and constant thrust once the entire motor powers up. If we have ignited it here, we might get some thrust up here, we might get some thrust down there, and then all of a sudden we have uneven thrust. In order to ignite it, we actually stick a bell wire all the way up the butt, all the way into the end of the nozzle, and there's a little nichrome wire. Nichrome gets really hot when you run high current through it, and then on top of that, we put a tiny little piece of propellant. So that nichrome wire, and then we pump a bunch of amps through it. We pump a very high current through that wire. So the nichrome gets really hot, it's right up against that tiny little piece of propellant, so that piece of propellant ignites from the heat, and then the rest of that propellant burning ignites the rest of the motor. And then the rest of the motor ignites itself all the way down.
It's interesting because it seems it's very similar to the technique we use with Estes rockets.
Yep, it's very, very similar. The only difference is that little piece of propellant that we put on the end of it,
Right.
and ours tend to draw a lot more current.
Sure.
So ours are just designed for higher current,
Right.
but we actually can make lower current versions for them, which we have,
And
similar to the Estes igniters.
so you said you use a ham radio using the APRS?
Yep.
Yeah, right. That's here at Kopernik we've done a weather balloon
Yes.
camp, and we've used APRS to
Nice.
track and recover.
Yeah, and you guys do ham radio training here as well, right?
Right.
Awesome,
Yeah,
yeah. We're actually hoping to come here with a couple team members to get them certified as well.
Excellent.
So I'm not the only one who's sitting here using the radio.
All right, great. Any other questions here, or I don't see anything else on the on the chat.
Yeah.
So how did you start, where did you start with the rockets? Did you just start putting stuff together, or taking measurements, or doing math, or what?
All that.
Oh, okay.
So really one of the first things we needed to develop is the motor. So the rocket's really built around the motor. This is what's called a minimum diameter rocket. So really our rocket is a rocket motor with fins on the bottom and a nose cone slapped on top. Most of this is filled with propellant, and that propellant is right inside of our airframe, and our thrust chamber are the same tube. So some rockets have an airframe, and then inside you stick a motor. So your motor is a separate thing from your rocket. You put that in, it's mounted inside, and it fires. Ours are not. Our motors are built directly into our rocket. It's a simplified approach. So that means we need to be able to have our motors working before we can really build our rockets. So that, in conjunction with our simulations, took a while to develop, so that's something we started very early on. We've been doing motor tests for over a year now, and rockets have been within the last half year. With that said, we also built smaller scale rockets. Some of the team members went ahead and got their level 1 certification from Tripoli as well, just so we can see, how does the rocket work? Because I built a bunch of rockets myself, but this is a whole other ballpark when you're building them from scratch, not from a kit. So frankly, we dove into it head first. Anything that had to do with rocketry, we started just trying to get our hands dirty, try to learn as much as we can. We wanted to fail fast and fail early.
All right. Unless there are any other questions, I want to thank you, Jacob, and Stephen for bringing Jacob, and also making us aware of all that the Triple Cities Makerspace offers here, to the Triple Cities. And so for those of you who are, again, who are new, definitely check out the Makerspace and see what they have to offer. I'll just promote that, Kopernik is doing our own Rocket Fest on a smaller scale, for sure. We already have, I think, 96 rockets.
That's awesome.
Set to launch on July 11th, and some people will be actually coming down to Barnes & Noble tomorrow to pick up their kits and build them at home and take them.
That's great.
So, anyway, so thank you very much, I appreciate it. I don't know, what's this guy's doing outside? Yeah, it's, so as predicted for tonight, but, for those that did come in and pay for their admission, we can give you a card to come back on another day, so, anyway, thank you much, and, thanks
you,
for
guys.
those watching on the live stream. And we'll, look forward to having you back to see the next chapter.